Hey on-demand astronomers, this is Julian from Cam10. I would like to share with you today how to build cameras for astronomy. I've built two little cameras for astronomy based on the MT9M001 sensor, which is a sensor from Micron Technology. The resolution is 1280 by 1024. It can do 30 fps, and this is a CMOS sensor with 5.2 micrometers pixel size. This is a black and white sensor, and these cameras are intended to be used for auto guiding or planetary imaging. I found the wiring diagrams for these cameras on the astroccd.org website and the Astropolis forum, which is a forum from an astronomy club from Kiev, an Ukrainian astronomy club. So I built the first camera based on a virtual COM port. The main advantage of this camera is that it works on all operating systems because all of the OS have COM drivers. But at first this camera wouldn't work, so I built a second camera. The second camera is based on the ASCOM driver. It was a little more complicated because it was an old version from 2015, but I've managed to get it work, and I will explain how I did that. So I worked again on the first camera and I've managed to fix it. So I will use this camera for planetary acquisition. The main advantage for the ASCOM version is that we can use it for auto guiding. So I worked quite a bit for the first camera with the virtual COM port. I built a 3D designed box with the FreeCAD software. After that I will 3D printing this box and adapt the PCB from Astropolis. For the second one with the ASCOM driver, there was missing a track on the PCB. I've seen a guy on the Astropolis forum which found that and add a wire to correct it. So I've worked on the PCB and redesigned all the PCB to add this missing track, and I added two holes to mounting a heatsink to cooling the sensor. Most of the users that build these cameras use the metal box to cooling the sensor, but I found that quite difficult to make, and we must machine a copper cylinder, which is not very easy to do at home. So I found less difficult to redesign the PCB and add a heatsink like this. This is a chipset heatsink. You can find it on AliExpress. As you can see, that make a clean box. I've also add mounting holes to mount the PCB on a box that I had designed on the FreeCAD software. Then I 3D printed it. So I've put all that stuff on the description below. You can download the software, the drivers. There is also the gerber files to order the PCBs. There is the STL files to order the box or printing by yourself if you own a 3D printer. We're gonna see how to solder the electronic components. This is CMS components, so they are very small. Some of these components, like resistors or capacitors, measure about 2 by 1 millimeters. I'd never solder the electronic component like that, and don't be afraid with this work, because it's quite easy, but you must equip yourself with magnifying glasses like this, or a microscope that you can plug on a smartphone or a PC. You must have a classic solder iron and a hot air to do the teeny soldering. We're gonna see that the price of these cameras are very affordable compared to the market cameras, and the main purpose is auto guiding, and what we need for auto guiding is a very sensitive camera to catch a star and keep tracking it. And we're gonna see that these cameras are very sensitive and can do the job. So for the soldering, there is several techniques. For the small resistances, you can drop a small amount of alloy on the pad. Then you take the resistor with a tweezer. I advise an inverted tweezer. These tweezers take the component when you release it and release the component when you press on it. So you hit the alloy to place the resistor and then you solder the other side. Another technique is to place some soldering paste on the pads and place the component and melt it with the hot air iron. There is also some components with several pins. You solder one pin to take it in place, and then you solder the other pins, and you can use some soldering paste to solder the teeny pitch like these components for microcontrollers. You can finish with a classic iron to cut the bridges. After that, you're gonna check the solders by using a magnifying glass, or if you are an astronomer, you can use an eyepiece of your telescope, like 25 millimeters. You can take it upside down, and that make a very magnifying glass. About the sensor, the first camera I built wasn't working because the sensor was defective. The first one that I had ordered seemed to be gold plated on the pins. The solder wasn't hung on the pins and these pins wasn't tinted. The logo on the back side was empty and this was a bad sensor. I replaced it by another reference with another logo like this with a circle. The pins on this one was tinted and it was much easier to solder. I just had to put some soldering paste on the pins and the pads and heat it with the classic iron. So I advise you to check the appearance of the sensor on the order. You have to remember to check the soldering by using a multimeter in home position. You can find some needles to adapt on your multimeter to check the teeny soldering. There is also some very useful stuff like this. This is an automatic checker for components. You plug your component on this, press test, and it tells you that it's a resistor or capacitor with the value associated with it. So I let you take a look at the following to see how I soldered these teeny components. So there is some components with a direction. You can check the data sheet to see for the quartz, for example, where the crystal is connected. For other components like capacitor, there is also a direction. Only for polarized capacitors, there is a plus and a minus on the component and the notch, and there is a line or a point on the PCB. For the resistors, there is no particular way, and for microcontrollers, there is a dot on the PCB and on the component. So we're gonna take a look now how the cameras are built. Here we have the completed PCB for the ASCOM version camera. Here we have the heatsink that we're mounting on the holes. And I have this ring that is normally intended for the Canon DSLR. And we have on it an M42 thread, not to be confused with the T2 for astronomy. So I have to put an adapter ring. So I have the board that will come on the ring. Obviously I have to drill holes in front of the board holes, and all that will come on this box with screws and springs behind the board and the ring. For the heat conjunction between the sensor and the heatsink, I've built a little copper disc that I cut on a cylinder that I've bought on AliExpress. We're gonna see later how I have managed to have the two-phase parallels on the disc. I've put some little wedge, 3mm thickness, on the glued on the board to have the heatsink passing over the electronic components. I've sanded the heatsink to have a mirror aspect on it and to have the best contact for the thermal conductivity. So we're gonna see now how I've built the little copper cylinder. So I've used a wooden piece that I've drilled at the diameter of the cylinder. I've put the cylinder on the hole, and behind I've put a bolt to tune the deepness. I've cut it and I've sanded it until to have a very flat side. I've controlled the thickness several times and I've adjusted it with the bolt, and at the end I've extracted when the thickness was okay. I've taken care that there is a little space between the sensor and the cylinder and the heatsink. When you move it, you hear a sound. This little space is to not to have constraint because of the dilatation, because the copper can expand with the heat and destroy the sensor soldering. I've cleaned up all that with isopropyl alcohol, and I've put some cryonote, which is actually one of the best thermal paste. I've put the thermal paste between the sensor and the cylinder, and between the cylinder and the heatsink, so the heat will be well conducted from the sensor to the heatsink to have an efficient cooling. When it's done, the cylinder no longer moves because the thermal paste is in the little gaps. By the way, I then replaced the cylinder with a larger one, which filled the hole in the PCB well to optimize the contact surface. Then I fixed an unused PCB on the ring to align a hole on the existing hole, and I drilled on the 2mm. Two components are a little too high, this one and this one, but mostly this one. When you put the ring on the box, it is in contact with these components, so I have to sand the ring until it no longer be in contact. So here we are mounting the camera. You put the PCB on the box and let the heatsink and USB port go into the holes. The tolerances on the nut holes were limited, so I've put the nut like that. So here we have the little springs that goes between the PCB and the ring, mounting on the screws. At this time we have to tighten the 4 screws and the camera is ended. So here we have the adapter ring for the ASCOM camera. On one side we have the M42 thread, which is a 42mm diameter with a 1mm thread. And on the other side we have the T2 thread, which is the standard for astronomy, which is also a 42 mm diameter, but with a 0.75 mm thread. For the second camera, for the thermal dissipation, I've used an aluminium piece of 1.5 mm thickness. I've cut it like a round at the diameter of the hole in the PCB. I've put some thermal paste on the sensor. I've put this disc on the hole, and then again some thermal paste, and I've put a heatsink sticker, and I've put also a heatsink on the microcontroller that hit a little. And here we can see the PCB of this camera on the T2 ring that will be used for the mounting. Here we have the conversion PCB with the heatsinks and the USB cable. So here we have all what we need for the mounting: the nuts, the washer, the screws, the camera conversion, a watch glass 43 mm diameter, a T2M42 adapter, the 3D printed pieces for this camera. We have the body, a ring and the lid, and some epoxy resin. So first thing, we take out the ring of the adapter. It has a T2 thread. So we take a look at the camera's body and we spot on the two holes that are near the edge, right here. And we're gonna glue the ring on the opposite side with epoxy resin. So we mix the two components. We have to do that quickly because this resin is a 2-minute hardening. We take out the overflow because there is a second piece that fit together, and we don't want that there is a space between the ring and this second piece. Then I glue this nut into the second piece that will fit into the camera body. This nut is intended to fix this ring into the camera body. I use the longer screw and we wait until it's fixed. Then I placed the 3 nuts into the holes on this ring. These 3 nuts will be behind the glass disc. So I take out the 20 mm screw. It will no longer be used. The resin is dried on the camera body. The resin can be cleaned with isopropyl alcohol. You can find it on the internet or a DIY store. Then I glued the glass disc over the 3 nuts on the little space. Then we take out overflow and clean up with isopropyl alcohol. Then we clean the maximum dust and place the camera over the ring. Take care that this little squared shape is on the whole side. Then we place 3 washers and 3 screws, and we screw all that on the nuts we placed before. Then we place the ring and the camera body. We fix the central ring with the 10 mm screw that screw into the nut we glued before. I glued the 2 nuts into the lid. Then we place the lid over the camera body. There is no need to glue the USB connector because the soldering pins for ground prevent it to go up. As you can see, I can plug and unplug the USB cable without any issue. Let's go now with the software part with the ASCOM camera. So to flash the firmware on the camera, you plug it on your computer and you're waiting for the driver installation. So here I hadn't soldered yet the sensor, but that's not a problem. Then we go to the FTDI website to download the driver to replace the default driver installed by Windows. So you can go here to download the drivers. So we follow the instruction on the screen, and when it's finished, you click on Finish. Then you go on the device manager, you go to the USB and found the USB serial converter A and B, and you uncheck the box for both. You have to uncheck the virtual COM port on these two parts. So we have to flash now the firmware of the board with this utility ft-prog. You can find it also on the astroccd.org here. So the file to flash on the camera is found on the astroccd.org. This is this file, cam10.ept, but you can find all that files on the description of this video. Then you open the mprog program, and then you go to Device, Scan. We can see here the board is detected. Then you can go to Tools, Read, and then you can read the content of the EEPROM. We can see here the EEPROM is empty because we have not programmed it yet. Then you go to Open. You open the file to flash into the board, cam10.ept, and then you go to Device Program, and when it's finished there is a message, program serial number cam10. Then you go to Read, and we can see here there is information, new information in the EEPROM, and we can see cam10, then the EEPROM is programmed. Then you can go to File, Exit. Now you can download the viewer here. This is the viewer used for this camera. Then we have the last ASCOM driver you can download here. This is the 0.5 version. When you click on the driver link and you scroll down, we have the installation sequence. We can see here that we have to install the framework from Microsoft version 3.5 SP1 or later. The ASCOM platform, we have to connect the camera, install the driver. That's done. We can flash the board with the mprog utility. That's done. And we have to install the ASCOM drivers. We can find the last version of the ASCOM platform on the ASCOM website. This is the 6.6, but I had to uninstall this version because the 6.2 was better for several software. So this is the website page to find the framework. Download the driver 0.5 ASCOM and the driver installation. So now you can use the viewer to use your camera in acquisition mode, but you can also use it in ASCOM mode with the ASCOM driver in your auto-guiding software. As you can see, there is many interrogative points in this interface. This is because this software is an Ukrainian software, but you can find the sources files in astroccd.com. So I've managed to translate the interface. You can find it in the description. According to astroccd.com, the ASCOM Cam10 camera is supported by SharpCap version 2.6. Here we have the version 3 that works perfectly. This is the oldest version we can download on the website, but I've downloaded also the brand new version 4.1 that works as well. Here we have Nebulosity, which was the software from Stark Labs. This software is now open source and freeware. Its new name is Open Nebulosity, and this is the version 1. So all these softwares wouldn't work on my rig with the last ASCOM platform. That's why I downgraded it on the 6.2 version. Now we take a look at the auto-guiding software. We can encounter problems with PHD2. Here I have opened PHD2 and I choose the ASCOM camera. Then I click on Connect All. Then I cycling to have a picture. As you can see, all is white, but it can be black or with a bad setting. We can see the camera setting icon is grayed out. We have no access to the camera settings. We can do anything, moving the slider, changing the exposure time. As you can see, the recording is still white. So for now we have no access for the driver in PHD2, but we have PHD1, which is the old software. And then if I click on ASCOM camera, OK, click on the ASCOM driver, OK, we have here the driver, and we can setting up the camera with this software. So if we click on cycling, we have the exact same blank screen, but we see the gain was at the maximum. So if I set the gain with a lower value and try to move the other sliders, we can have a start of an image. With PHD2 was probably saturated. So here, if I lower the exposure time, we can see we have a correct image. At this time the sensor is quite dirty. I don't have cleanup for now. So here we can see the target, so we can click on stop and close PHD1 and open again PHD2. So we click on connect all, cycling, we have a blank image, but we can see a little the target. I lower the exposure time and we can see the image is appearing, and by moving the slider we have the exact same picture as for PHD1. Here we have the viewer. I've translated from Ukrainian. It's acquiring. When you see a peak like that, it means that it's overexposed. Then we can lower the exposure time and we can see the picture is appearing. I can lower here the gain, which was at the maximum, and we can here increase the exposure time until we have a good picture. We can use this viewer to focus on the star before starting the auto-guiding software. But we keep in mind that we must use the ASCOM driver to use the auto-guiding in PHD2. So to set up the camera we must use PHD1 before using PHD2. So now let's talk about the conversion. To flash the firmware on the board, we have to use this USB key. This USB key is used to program the chips coming from ST Microelectronics manufacturer. That's gonna be more simple. We just have to flash the firmware. There is no driver to install. We have to plug 3 wires, the SW clock, the SW DIO and the ground. So we can see here I've plugged 3 different cables on the USB key. They go to a little connector that I plug on the programming port in the board. So we have to plug it on this connector. So I zoom in here on the connector to let you see how to plug the 3 wires on this connector. On the left, this is the ground. There is no error with the color. The left is the ground, the center is the data, and the right wire is the clock. We have to connect the ground on the ground, the data on the SWIO, and the clock on the SW clock. So now let's program the board. I've plugged a USB cable on the board. I plug the USB key on the USB and I plug the USB to feed the board. If you want to download all what you need directly on the forum, you go to the 188 page. We can do a big thank to Grim that create all these cameras, a passionate astronomer. Here we have the diagram. So we have pictures of the camera, and we can see here that the solder is a little bit more long. This is because the PCB has a fault. Let's take a look at that. Here we have the PCB of the conversion, and this is this leg. And if you take a look, you see there is a little space that we have to fill by scratching the via and make a bridge. And we have another error here. This is these two capacitors, number C4 and C3. There is a mistake on the list. You can download the list here, and you can see on the list these two capacitors with the box 1206 here, the C3 and the C4. It's indicated to use 106 capacitors, which are 10 microfarads capacitors, but this is a mistake. Grim will talk about it later in the forum. The right value is 100 microfarad. We have the gerber file to download the PCB. We have the viewer to take pictures with the camera. And here you have the firmware to be flashed in the board. We can take a look about the message from Grim about the capacitors. Someone asked why these capacitors are taller, and in answer that it is because these ones are 100 microfarads and there is a mistake in the diagram. So now we're gonna take a look about the board flashing for this COM camera. We have to download the utility from ST Microelectronics. We can't download it directly. We have to ask it by email, and we receive a link to download. So I have the USB key plugged into the board, and I open the software, click on Target Connect. I have the board detected and the firmware is displaying here. So we click on File, Open File. We're looking for the file. This is the file to be flashed into the board. This is exactly the same because I already flashed this board. We can click on Target and erase only to erase the board, or Program and Verify. You click on Program and Verify, Start, and the board is flashed. We have the message that it says that it's okay. And the checking is also okay. So now we can use the viewer. We just have to connect the camera, click on Get Image, and we have the image. We can change here the exposure time. I have no camera lens here. I have the camera placed on the fan grid of my PC. That is what we can see on the screen. We also can take sequences by clicking here on Start Sequence. Here we have the camera finished, mounted in its box. I've mounted it in the guide scope, and I'm aiming here my favorite target. So on this viewer there is no sliders. We have to put the gain on the box and click Apply. We can see here the conversion of this camera making planetary acquisition. And the ASCOM version camera making auto-guiding, but also working for acquisition with the viewer. So this is the end of this video. I hope you enjoyed it. You have now all what you want to make your own camera. If you have something to add, you can drop it in the comments. If you are a software developer and interested by improved drivers, there is the source driver in the package. That will be great because there is some limitations and I have not the skills to do that. So for now, I wish you all good skies.